Beneath the frozen crusts of Europa and Titan, two of our solar system's most enigmatic moons, lie hidden oceans that could potentially harbor life. These icy worlds, with their alien landscapes and extreme environments, are beckoning us to uncover their secrets. In the coming years, ambitious missions will venture into these distant realms, not just to explore, but to search for the most profound question of all: are we alone in the universe? Join us as we dive into the future of space exploration and the thrilling quest for biosignatures in the outer solar system. The enigmatic moons, Europa and Titan. Beneath the icy crust of Europa, a moon of Jupiter, lies a global ocean that could harbor more than twice the amount of water found in all of Earth's oceans. This ocean is shielded from the harsh radiation of space by a layer of ice that is thought to be between 15 to 25 kilometers thick. The surface of Europa is a tapestry of streaks, ridges, and chaotic terrain, all sculpted by the tidal forces exerted by Jupiter's immense gravity. These forces generate heat, which may drive hydrothermal vents on the ocean floor, creating environments that could support life. Scientists are particularly interested in Europa's biosignatures, which are indicators of past or present life. These could include certain minerals, organic compounds, or even microbial fossils. The Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of Europa and investigate whether the icy moon could harbor conditions suitable for life. The spacecraft will carry a suite of 9 scientific instruments, including cameras, spectrometers, and a radar system that will peer beneath the ice to map the subsurface ocean. Titan, the largest moon of Saturn, is a world of contrasts. It has a thick, nitrogen-rich atmosphere, the only other stable, significant atmosphere in the solar system besides Earth's. The surface is a complex mix of organic compounds, with vast dunes of hydrocarbon particles and lakes and seas of liquid methane and ethane. Beneath this alien landscape, there may be a subsurface ocean of liquid water, making Titan another promising candidate in the search for extraterrestrial life. The Dragonfly mission, planned for launch in 2026, will send a robotic rotorcraft to explore Titan's surface. This drone-like vehicle will be able to fly from one location to another, sampling the atmosphere and surface materials along the way. One of its key objectives is to search for biosignatures, which on Titan could include complex organic molecules that might hint at the presence of life. The mission will also investigate the moon's habitability, studying its atmosphere, surface processes, and subsurface ocean. A brief history of exploration. The quest to understand Europa and Titan, two of the most enigmatic moons in our solar system, has been driven by the tantalizing possibility of finding extraterrestrial life. Europa, Jupiter's icy moon, has captivated scientists with its global ocean hidden beneath a thick ice shell. Early flybys by Voyager 1 and 2 in the late 1970s provided the first tantalizing hints of this subsurface ocean, revealing a surface crisscrossed with dark streaks and cracks. These features suggested a dynamic environment, possibly fueled by tidal forces from Jupiter's immense gravity. The Galileo mission, which orbited Jupiter from 1995 to 2003, confirmed the presence of this subsurface ocean and provided detailed images of Europa's icy surface. The data from Galileo hinted at the possibility of hydrothermal vents on Europa's ocean floor, similar to those found on Earth, which could provide the necessary energy and nutrients for life. Titan, Saturn's largest moon, presents a starkly different yet equally intriguing environment. Unlike Europa, Titan is shrouded in a thick, hazy atmosphere composed primarily of nitrogen, with a surface dotted with lakes and rivers of liquid methane and ethane. The Cassini-Huygens mission, which explored the Saturn system from 2004 to 2017, provided unprecedented insights into Titan's complex chemistry and geology. The Huygens probe, which landed on Titan's surface in 2005, revealed a landscape remarkably similar to Earth, complete with dunes, rivers, and lakes. The data from Cassini and Huygens suggested that Titan's surface is geologically active, with cryovolcanoes and methane rain shaping its landscape. The presence of complex organic molecules in Titan's atmosphere and on its surface has led scientists to speculate about the potential for prebiotic chemistry, the chemical processes that precede the emergence of life. The search for biosignatures, or signs of life, has been a central focus of these missions. On Europa, scientists are particularly interested in the chemical composition of the subsurface ocean, which could contain essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The presence of these elements, along with a source of energy, could create the right conditions for life. On Titan, the focus is on the complex organic molecules that rain down from the atmosphere and accumulate on the surface. These molecules could potentially serve as the building blocks for life, although the extremely cold temperatures and lack of liquid water make it a challenging environment for life as we know it. Future missions aim to build on these discoveries, using advanced instruments to search for definitive signs of life in these icy worlds. The allure of the outer solar system. Beneath the frozen crusts of Europa and Titan, two of the most enigmatic moons in our solar system, lie vast oceans that have captivated scientists and space enthusiasts alike. Europa, a moon of Jupiter, is encased in a thick layer of ice, potentially hiding a global ocean twice the volume of Earth's. This icy shell, scarred by cracks and ridges, tells a tale of a dynamic world where tidal forces from Jupiter's gravity flex and crack the surface. Beneath this frozen expanse, an ocean of liquid water, possibly with more water than all of Earth's oceans combined, could harbor conditions suitable for life. The allure of Europa lies in its potential to host extraterrestrial life, making it a prime target for future exploration. Titan, the largest moon of Saturn, presents a different yet equally intriguing icy environment. Unlike Europa, Titan's surface is not dominated by water ice, but by a thick atmosphere and a complex chemistry involving hydrocarbons. Beneath its icy crust, Titan is believed to have a subsurface ocean of liquid water and ammonia. The moon's surface is dotted with lakes and rivers of methane and ethane, creating a landscape eerily reminiscent of Earth's hydrological cycle, but with a twist of exotic chemistry. This unique environment makes Titan a fascinating subject for studying prebiotic chemistry and the potential for life to emerge in conditions vastly different from Earth's. The search for biosignatures, or indicators of life, is a driving force behind the exploration of these icy worlds. On Europa, scientists hope to find evidence of hydrothermal vents on the ocean floor, similar to those found in Earth's oceans, which could provide the energy and nutrients necessary for life. The Europa Clipper mission, set to launch in the coming years, will conduct detailed reconnaissance of Europa and investigate whether the icy moon could harbor conditions suitable for life. Titan, with its rich organic chemistry, offers a different avenue for the search for life. The Dragonfly mission, planned for the mid-2030s, will send a drone to explore Titan's surface, studying its chemistry and searching for signs of past or present life. Both Europa and Titan present unique challenges and opportunities for scientific discovery. Their icy environments, while harsh and unforgiving, hold the promise of unlocking some of the most profound questions about our place in the universe. The allure of the outer solar system lies not just in the potential for finding life, but in the fundamental understanding of planetary processes and the origins of life that these missions will provide. As we venture further into the outer solar system, the mysteries of Europa and Titan beckon, offering a glimpse into the possibilities that lie beyond our home planet. Europa, a frozen ocean world. Europa, one of Jupiter's 4 largest moons, is a captivating world encased in a global ocean of ice. Beneath its frozen surface, scientists strongly suspect a subsurface ocean of liquid water, potentially harboring more than twice the volume of Earth's oceans. This icy shell, which can be as thick as 1525 kilometers, is crisscrossed by dark streaks and fractures, hinting at a dynamic and geologically active environment. The surface temperature hovers around -160 degrees Celsius -256 degrees Fahrenheit, making it one of the coldest places in our solar system. Despite these harsh conditions, the potential for a habitable environment lies beneath. The icy environment of Europa is a stark contrast to Earth's oceans, yet it shares some intriguing similarities. The ice shell is not static. It is subject to constant bombardment by radiation from Jupiter's magnetic field, which can alter the surface chemistry. This radiation also creates a tenuous atmosphere composed primarily of oxygen. Beneath the ice, tidal forces from Jupiter's gravity generate heat, which could maintain a liquid water ocean. This subsurface ocean is thought to be in direct contact with a rocky seafloor, providing essential minerals and energy sources that could support life. The interaction between the ocean and the seafloor is a critical factor in the search for biosignatures, as it mirrors the conditions found in Earth's deep-sea hydrothermal vents, known to host diverse ecosystems. Scientists are particularly interested in Europa's biosignatures, which are indicators of past or present life. The Europa Clipper mission, set to launch in the near future, aims to conduct detailed reconnaissance of Europa and investigate its habitability. The spacecraft will carry a suite of advanced instruments designed to analyze the Moon's surface and subsurface. One key instrument is the Europa Imaging System, EIS, which will capture high-resolution images of the surface, revealing details about its composition and geology. Another crucial tool is the Europa Thermal Emission Imaging System, ETHEMIS, which will map the temperature variations on Europa's surface, providing insights into its thermal properties and potential activity. The search for biosignatures will also involve studying the Moon's thin atmosphere and any plumes of water vapor that might be venting from the subsurface ocean. The mass spectrometer, MASSPEX, and the surface dust mass analyzer, SUDA, will analyze the composition of these plumes, looking for organic molecules and other potential signs of life. Additionally, the radar for Europa assessment and sounding, ocean to near surface, REASON, instrument will use radar to penetrate the icy shell and study the structure of the subsurface ocean. By combining data from these instruments, scientists hope to gain a comprehensive understanding of Europa's potential habitability and the possibility of life existing beneath its icy surface. Titan, a world of hydrocarbons and mystery. Saturn's moon Titan is a captivating enigma, a world where hydrocarbons flow like water and mysteries abound. Beneath its hazy, nitrogen-rich atmosphere, rivers and lakes of methane and ethane carve landscapes eerily reminiscent of Earth, yet utterly alien. The surface is a frigid -179 degrees Celsius, a deep freeze that would instantly liquefy the oxygen in our lungs. This cryogenic environment is home to a complex chemistry that scientists believe could harbor the building blocks of life. Titan's hydrocarbons are not just a scientific curiosity, they are a potential pathway to understanding the origins of life. The Moon's atmosphere is a vast chemical reactor, where sunlight and cosmic rays break apart nitrogen and methane molecules, leading to the formation of complex organic compounds. These compounds rain down onto the surface, creating a rich, prebiotic soup. The Cassini-Huygens mission revealed that Titan's surface is dotted with dunes of organic material, possibly mixed with water ice. This interplay of hydrocarbons and water ice is a tantalizing hint that Titan might hold clues to how life first emerged. The search for biosignatures on Titan is a top priority for future missions. Scientists are particularly interested in the Moon's subsurface ocean, which lies beneath its icy crust. This hidden sea, likely composed of water mixed with ammonia, could provide a stable environment for life. Future missions, such as NASA's Dragonfly, aim to explore Titan's surface and atmosphere in greater detail. Dragonfly, a robotic rotorcraft, will sample various locations, searching for signs of past or present life. The mission's advanced instruments will analyze the composition of Titan's atmosphere, surface, and subsurface, providing unprecedented insights into this enigmatic world. Titan's icy environments present unique challenges and opportunities for exploration. The Moon's thick atmosphere and low gravity make it an ideal candidate for aerial exploration. Future missions could include balloons or drones that can navigate Titan's skies, collecting data and samples from diverse locations. The icy crust itself is a subject of intense study. Scientists believe that cryovolcanoes, which erupt a mix of water ice and ammonia, might be active on Titan. These features could provide direct access to the subsurface ocean, offering a chance to study its composition and potential habitability. The interplay of hydrocarbons, water ice, and potential cryovolcanic activity makes Titan a dynamic and intriguing world, ripe for exploration and discovery. The scientific imperative. Europa, one of Jupiter's moons, is a captivating world of ice and mystery. Beneath its frozen surface, scientists strongly suspect a global ocean of liquid water, potentially harboring more than twice the volume of Earth's oceans. This icy shell, cracked and streaked with reddish-brown lines, is a testament to the geological activity driven by tidal forces from Jupiter's immense gravity. The search for biosignatures in this harsh environment is a driving force behind future missions. Scientists aim to analyze the composition of Europa's ice and any potential plumes of water vapor that might erupt from its surface. These plumes, if confirmed, could provide direct samples from the subsurface ocean, offering clues about the potential for life. Titan, Saturn's largest moon, presents a different yet equally intriguing icy environment. Unlike Europa, Titan's surface is shrouded in a thick, hazy atmosphere, primarily composed of nitrogen with a smattering of methane. This atmosphere creates a cycle of precipitation, erosion, and liquid flow that is eerily reminiscent of Earth's water cycle, but with methane and ethane taking the place of water. Beneath its icy crust, Titan may also harbor a subsurface ocean of liquid water, adding to its potential for harboring life. The search for biosignatures on Titan focuses on understanding the complex organic chemistry occurring in its atmosphere and on its surface. The presence of tholins, complex organic molecules formed by ultraviolet irradiation of simple organic compounds, could provide insights into the prebiotic chemistry that might lead to life. The scientific imperative for exploring these icy worlds is rooted in the quest to understand the origins of life and the potential for life beyond Earth. Europa's subsurface ocean, shielded from harmful radiation by its icy crust, could provide a stable environment for life to emerge and thrive. The study of its ice composition and any potential plumes could reveal the presence of essential elements and compounds necessary for life. Similarly, Titan's rich organic chemistry and potential subsurface ocean make it a prime target for astrobiological research. Understanding the processes that shape these icy environments can shed light on the conditions that might lead to the emergence of life elsewhere in the universe. Future missions to Europa and Titan are equipped with advanced instruments designed to probe these icy worlds in unprecedented detail. For Europa, missions like NASA's Europa Clipper aim to perform close flybys, mapping the moon's surface and analyzing its composition. The Europa lander, a proposed follow-on mission, would directly study the surface, searching for biosignatures and signs of recent geological activity. On Titan, the Dragonfly mission, a robotic rotorcraft lander, will explore diverse locations, studying the moon's atmosphere, surface, and subsurface. These missions will provide a wealth of data, advancing our understanding of these enigmatic worlds and their potential to harbor life. Technological challenges and innovations. Europa, one of Jupiter's moons, and Titan, the largest of Saturn's moons, present some of the most extreme and intriguing environments in our solar system. Both are icy worlds, but their surfaces and subsurface oceans hide secrets that could rewrite our understanding of life beyond Earth. To explore these enigmatic places, scientists and engineers face a myriad of technological challenges, driving innovations that push the boundaries of what's possible. Europa's surface is a vast, frozen expanse, cracked and streaked with reddish-brown lines that hint at a subsurface ocean beneath. This ice shell, estimated to be 10 to 25 kilometers thick, is subject to intense radiation from Jupiter's magnetosphere. Any mission to Europa must contend with this harsh environment, which can degrade electronics and damage sensitive instruments. To mitigate these effects, engineers are developing radiation-hardened electronics and innovative shielding materials. Additionally, the extreme cold requires heating systems to keep instruments operational, often relying on radioisotope thermoelectric generators, RTGs, for power. One of the most promising innovations for exploring Europa is the development of autonomous underwater vehicles, AUVs, capable of navigating its subsurface ocean. These robots would need to be highly adaptable, able to map the ocean floor, collect samples, and search for biosignatures, molecular indicators of life. The challenges are immense, including designing vehicles that can withstand the immense pressure of Europa's ocean and communicate through the thick ice shell. Researchers are exploring various communication methods, such as acoustic signals or even neutrino-based communication, to overcome this hurdle. Titan, on the other hand, is a world of hydrocarbons, with lakes and rivers of methane and ethane dotting its surface. Its thick, hazy atmosphere is rich in organic compounds, making it a prime target in the search for the building blocks of life. The Cassini-Huygens mission provided valuable data, but future missions aim to delve deeper. One of the key challenges is designing instruments that can operate in Titan's cryogenic temperatures, where the surface is a chilly -179 degrees Celsius. Engineers are developing advanced materials and insulation techniques to protect sensitive equipment. Innovations in power generation are also crucial for Titan missions. Solar power is impractical due to the distance from the sun and the thick atmosphere. Instead, missions like the proposed Dragonfly drone will likely rely on RTGs. These generators provide a steady power supply, essential for long-duration missions. Another challenge is navigating Titan's complex terrain, which includes dunes, mountains, and cryovolcanoes. Advanced autonomy and AI systems are being developed to enable drones and rovers to make real-time decisions and avoid hazards. Both Europa and Titan present unique opportunities for scientific discovery. The search for biosignatures is a central focus, requiring highly sensitive instruments capable of detecting even trace amounts of organic molecules. Mass spectrometers, gas chromatographs, and advanced imaging systems are being refined to meet these demands. Additionally, scientists are developing new methods for analyzing samples in situ, reducing the need for sample return missions, which are complex and costly. In summary, the technological challenges of exploring Europa and Titan are driving innovations that will shape the future of space exploration. From radiation-hardened electronics to autonomous underwater vehicles and advanced power systems, these advancements are paving the way for a deeper understanding of our solar system and the potential for life beyond Earth. The icy environments of these moons, with their subsurface oceans and complex chemistries, offer a tantalizing glimpse into the possibilities of habitability in the cosmos. Mission planning, from concept to reality. The journey to explore Europa and Titan, two of the most intriguing moons in our solar system, begins with meticulous mission planning. Scientists and engineers embark on a complex process that transforms initial concepts into tangible missions, aiming to unravel the secrets hidden beneath their icy surfaces. Europa, with its vast subsurface ocean, and Titan, with its Earth-like cycles and hydrocarbon lakes, present unique challenges and opportunities for scientific discovery. Europa's icy shell, estimated to be 1525 kilometers thick, conceals an ocean that could hold twice as much water as Earth's seas. Planning missions to this moon involves developing technologies capable of penetrating or navigating this icy barrier to access the subsurface ocean. Instruments must be designed to withstand extreme radiation levels, as Europa orbits within Jupiter's intense magnetic field. Scientists are particularly interested in searching for biosignatures, which are indicators of past or present life. These could include specific chemicals, minerals, or even microbial fossils. The Europa Clipper mission, for instance, will conduct detailed reconnaissance of Europa and investigate whether the icy moon could harbor conditions suitable for life. Titan, on the other hand, boasts a thick atmosphere and a surface rich in organic compounds. Its lakes and rivers of methane and ethane create a landscape eerily reminiscent of Earth, but with a fundamentally different chemistry. Mission planners focus on developing probes and landers that can survive the frigid temperatures, which average around -179 degrees Celsius. The Dragonfly mission, a rotorcraft lander, is set to explore Titan's diverse environments, searching for prebiotic chemistry and potential biosignatures. Understanding Titan's environment could provide insights into the early stages of life's development and the potential for habitability beyond Earth. Both Europa and Titan present formidable challenges, but the potential scientific rewards are immense. Mission planning involves a delicate balance between technological capabilities, scientific objectives, and budgetary constraints. Each mission is a testament to human ingenuity and our relentless pursuit of knowledge. As we venture deeper into the outer solar system, the icy moons of Europa and Titan stand as beacons of scientific discovery, beckoning us to uncover their mysteries and perhaps redefine our understanding of life in the universe. The role of robotic explorers. Robotic explorers are at the forefront of our quest to understand the icy moons Europa and Titan, offering unparalleled access to their harsh, alien environments. Europa, with its vast subsurface ocean hidden beneath a thick icy crust, presents a challenging yet tantalizing target. Robotic missions, such as NASA's upcoming Europa Clipper, are equipped with advanced instruments designed to penetrate this icy veil. These probes will map the moon's surface in high detail, using radar to peer through the ice and study the hidden ocean below. They'll also analyze the composition of Europa's icy shell, searching for signs of water plumes that could provide direct samples from the subsurface ocean. Titan, Saturn's largest moon, is a world of icy dunes and hydrocarbon lakes, making it a unique target for robotic exploration. Missions like NASA's Dragonfly, set to launch in the near future, will take advantage of Titan's Earth-like atmospheric pressure, which allows for the use of rotorcraft. These robotic explorers will navigate Titan's complex terrain, studying its methane lakes and icy landscapes. They'll search for biosignatures, looking for signs of past or present life in this cryogenic environment. The data collected will help scientists understand the chemical processes at play and assess Titan's habitability. In both Europa and Titan, robotic explorers face extreme conditions. Europa's surface is bombarded by radiation from Jupiter's magnetic field, requiring robust shielding for electronic components. Meanwhile, Titan's surface is incredibly cold, with temperatures around -290 degrees Fahrenheit, -179 degrees Celsius. Robotic missions must be equipped with specialized heating systems to operate in these frigid conditions. Despite these challenges, the potential scientific payoff is immense. These icy moons offer some of the most promising targets in our search for life beyond Earth. Robotic explorers, with their advanced instruments and resilient designs, are our best bet for unlocking the secrets of these enigmatic worlds. Human missions, dreams, and possibilities. Europa, one of Jupiter's moons, is a captivating world of ice and mystery. Beneath its frozen surface, scientists believe there's a global ocean of liquid water, potentially harboring more than twice the volume of Earth's oceans. This icy environment, with its cracked and ridged surface, is a tantalizing target for human exploration. The search for biosignatures, or signs of life, is a primary driver. These could include certain chemical imbalances, specific minerals, or even direct evidence of microbial life. The radiation environment around Europa is harsh, but not insurmountable. Understanding how to protect human explorers from this radiation will be a significant challenge, but one that could yield innovative solutions for future space travel. Titan, Saturn's largest moon, offers a different kind of icy allure. It's the only moon in our solar system with a substantial atmosphere, and it's rich in organic compounds. The surface is a complex mix of ice and hydrocarbons, with lakes and rivers of liquid methane and ethane. Human missions to Titan could focus on exploring these exotic landscapes and searching for biosignatures in this unique environment. The low gravity and frigid temperatures present considerable challenges, but also opportunities for scientific discovery. The search for life on Titan might not involve looking for water-based life as we know it, but rather, life that could exist in the methane cycle. Both Europa and Titan present extraordinary opportunities for human exploration and scientific discovery. The icy environments of these moons could hold clues about the origins of life in our solar system and beyond. The search for biosignatures is a unifying theme, driving our quest to understand these enigmatic worlds. Human missions to these moons would not only advance our scientific knowledge, but also inspire future generations to reach for the stars. The challenges are immense, but the potential rewards are even greater. From the radiation-bombarded surface of Europa to the methane lakes of Titan, these icy worlds beckon us to explore, to discover, and to push the boundaries of human achievement. Europa's ice shell, a barrier and a gateway. Europa, Jupiter's icy moon, presents one of the most enticing frontiers in our solar system for astrobiologists. Beneath its radiation-battered surface lies a global ocean, potentially harboring more liquid water than all of Earth's oceans combined. The ice shell, ranging from 15 to 25 kilometers thick, is both a formidable barrier and a tantalizing gateway to this hidden ocean. It's a cold, desolate landscape, crisscrossed by ridges and fractures, with temperatures plummeting to minus 160 degrees Celsius. Yet, beneath this frozen expanse, there's a world of liquid water, kept warm by tidal forces exerted by Jupiter's immense gravity. The ice shell's composition and structure are critical to understanding Europa's potential habitability. It's primarily made of water ice, but it's not uniform. There are regions of chaotic terrain, where the ice has broken apart and reformed, hinting at processes that might transport material from the ocean below to the surface. These areas are of particular interest, as they could contain biosignatures, molecules, or patterns that indicate the presence of life. Scientists have detected various salts and organic compounds on Europa's surface, which could have originated from the subsurface ocean. The ice shell, therefore, acts as a record, preserving clues about the ocean's composition and potential habitability. To access this ocean, future missions will need to overcome the challenges posed by the ice shell. One proposed method is to use a cryobot, a robotic probe designed to melt its way through the ice. This would be a slow process, taking years to reach the ocean. Once there, the cryobot could directly sample the water, search for biosignatures, and study the ocean's properties. Another approach is to study the ice shell itself, using advanced instruments to analyze its composition and structure. This could provide insights into the ocean's chemistry and the processes that transport material between the ocean and the surface. The search for biosignatures is a key focus of Europa exploration. Life, as we know it, requires liquid water, a source of energy, and certain chemical building blocks. Europa's ocean has the potential to satisfy all these requirements. The ice shell, therefore, is not just a barrier, but a gateway to a world that could harbor life. Future missions will build on the legacy of past explorations, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? Subsurface oceans, the quest for extraterrestrial life. Beneath the icy crusts of Europa and Titan, scientists believe vast subsurface oceans could harbor the ingredients for life. Europa, Jupiter's moon, is encased in a thick layer of ice, potentially concealing a global ocean twice the volume of Earth's. This ocean is kept liquid by tidal forces from Jupiter, generating heat through friction. Titan, Saturn's largest moon, also harbors a subsurface ocean, but its icy shell is mixed with organic compounds, creating a complex chemical environment. Both moons present unique challenges and opportunities for exploring the potential for extraterrestrial life. The icy environments of Europa and Titan are extreme, with temperatures plunging hundreds of degrees below freezing. Europa's surface is crisscrossed by dark streaks and fractures, hinting at a dynamic interaction between the icy crust and the underlying ocean. Titan's surface is even more enigmatic, with lakes and rivers of liquid methane and ethane. Beneath these alien landscapes, the subsurface oceans are shielded from harsh radiation, providing a potentially habitable environment. Scientists are particularly interested in these oceans because they may contain the necessary elements for life: water, energy, and organic compounds. The search for biosignatures in these subsurface oceans is a top priority for future missions. Biosignatures are indicators of life, such as specific chemicals or patterns that suggest biological processes. On Europa, scientists hope to find evidence of hydrothermal vents on the ocean floor, similar to those found on Earth, which could support chemosynthetic life forms. Titan's organic-rich environment offers a different avenue for exploration, with the potential for prebiotic chemistry leading to the formation of life. Future missions will use advanced instruments to analyze the composition of these oceans, looking for signs of life or the conditions that could support it. One of the most promising approaches to studying these subsurface oceans is through the use of robotic explorers. For Europa, NASA's Europa Clipper mission will conduct detailed reconnaissance, using a suite of instruments to study the moon's ice shell and subsurface ocean. The mission aims to determine the moon's habitability and identify potential sites for future exploration. For Titan, The Dragonfly mission will send a drone to explore the moon's surface and atmosphere, providing valuable data on its organic chemistry and potential for life. These missions represent the next step in our quest to understand the potential for life beyond Earth. Titan's atmosphere, a prebiotic laboratory. Titan, Saturn's largest moon, harbors a thick, nitrogen-rich atmosphere that serves as a captivating analog to early Earth. This atmosphere, 4 times denser than Earth's, is a complex chemical soup where sunlight and cosmic rays trigger reactions, creating a plethora of organic compounds. Methane, the second most abundant gas, plays a crucial role in this chemistry, breaking down and recombining to form a variety of hydrocarbons and nitriles. These processes paint a vivid picture of an icy world where prebiotic chemistry might be unfolding, offering scientists a unique opportunity to study conditions reminiscent of our planet's early days. The icy environments of Titan, with their rivers, lakes, and possibly even rain, provide a stark contrast to the arid landscapes of other moons. These cryogenic conditions, with temperatures around -290 degrees Fahrenheit, create a laboratory for studying low-temperature chemistry. The Cassini-Huygens mission revealed that Titan's atmosphere contains tholins, complex organic molecules that form when ultraviolet light strikes methane and nitrogen. These tholins settle onto the surface, contributing to the moon's orange hue and potentially providing the raw materials for life as we know it. The search for biosignatures in this context focuses on detecting these complex organics and understanding their formation pathways. One of the most intriguing aspects of Titan's atmosphere is the presence of molecular hydrogen and acetylene, which could potentially fuel methanogenic life if it exists. Scientists are particularly interested in the moon's polar regions, where the atmosphere is denser and chemical reactions might be more pronounced. The Dragonfly mission, planned for the mid-2030s, aims to explore these regions with a robotic rotorcraft, sampling different locations to search for signs of past or present habitability. By studying Titan's atmosphere, researchers hope to uncover clues about the origins of life on Earth and the potential for life elsewhere in the universe. The icy moon's unique chemistry offers a tantalizing glimpse into the processes that might have sparked life in our solar system and beyond. Landing on Europa, overcoming the challenges. Europa, Jupiter's icy moon, presents a tantalizing target for future space missions. Beneath its frozen surface lies a global ocean of liquid water, potentially harboring the ingredients for life. Landing on Europa, however, is a formidable challenge due to its harsh environment and the technological hurdles it presents. The moon's surface is a complex landscape of ice ridges, cracks, and chaotic terrain, all bathed in intense radiation from Jupiter's magnetic field. Navigating this treacherous terrain requires advanced autonomous systems and robust landing gear capable of handling the unpredictable surface. The icy environment of Europa is both a scientific goldmine and a significant obstacle. The surface is predominantly water ice, with a composition that includes frozen salts and possibly organic compounds. Beneath this icy shell, scientists believe there is a subsurface ocean that could be habitable. To access this ocean, a lander would need to overcome the challenges of drilling through the ice or finding locations where the ocean might be closer to the surface, such as in chaotic terrain or near suspected plumes of water vapor. The search for biosignatures, molecular patterns, or chemical signatures that indicate the presence of life would be a primary objective. Instruments would need to be highly sensitive and capable of detecting subtle signs of life in the icy material. Radiation is another critical challenge. Europa is embedded in Jupiter's intense radiation belts, which can damage electronic components and pose risks to any potential life forms. Shielding the lander and its instruments from this radiation is essential. Additionally, the extreme cold, with surface temperatures averaging around -160 degrees Celsius -256 degrees Fahrenheit, requires advanced thermal management systems to keep the lander's electronics and instruments operational. Power generation is also a concern, as solar panels would be less effective due to the distance from the sun and the radiation environment. Radioisotope thermoelectric generators, RTGs, might be a more reliable power source for long-duration missions. Overcoming these challenges requires innovative engineering and scientific approaches. Autonomous navigation systems would need to map the surface in real time, avoiding hazards and identifying safe landing sites. Advanced drilling or sampling technologies would be necessary to access the subsurface ocean or collect samples from beneath the icy surface. Robotic arms and sample analysis instruments would need to be designed to operate in the harsh conditions, with the ability to detect and analyze biosignatures. Collaboration between scientists, engineers, and mission planners is crucial to develop the technologies and strategies needed for a successful landing on Europa. The potential scientific discoveries, including the possibility of finding extraterrestrial life, make the challenges worthwhile. Exploring Titan's surface, drones, and balloons. Titan, Saturn's largest moon, presents a unique and captivating environment for exploration. Its surface is a complex interplay of organic materials and icy terrain, making it a prime candidate for studying prebiotic chemistry and potential habitability. The moon's dense atmosphere, rich in nitrogen and methane, creates a dynamic environment with Earth-like features such as dunes, rivers, and lakes. However, the extreme cold, with surface temperatures hovering around -179 degrees Celsius -290 degrees Fahrenheit, necessitates innovative approaches to exploration. Drones and balloons are at the forefront of proposed missions to Titan, offering unparalleled access to its surface and atmosphere. These aerial platforms can navigate the moon's dense atmosphere, providing a bird's-eye view of its diverse landscapes. Drones, equipped with advanced sensors and cameras, can traverse the icy dunes and explore the shores of methane lakes, gathering data on the composition and structure of Titan's surface. Balloons, on the other hand, can float at various altitudes, offering a broader perspective and the ability to study atmospheric phenomena and weather patterns. One of the primary goals of these missions is the search for biosignatures, indicators of past or present life. Titan's rich chemistry, including the presence of complex organic molecules, makes it a compelling target for astrobiological research. Drones and balloons can collect samples from the surface and atmosphere, analyzing them for signs of biological activity. They can also study the interactions between the surface and atmosphere, shedding light on the chemical processes that might lead to the formation of life. The icy environments of Titan present both challenges and opportunities. The moon's surface is covered in a layer of water ice, with a subsurface ocean of liquid water potentially harboring life. Drones and balloons can investigate the ice's composition and structure, providing insights into the moon's geological history and potential habitability. They can also explore the cryovolcanic features, where water ice and ammonia might erupt from the subsurface, offering a glimpse into the moon's internal processes. By studying these icy environments, scientists hope to uncover the secrets of Titan's past and its potential to support life. The search for biosignatures. Beneath the icy crust of Europa, Jupiter's moon, lies a global ocean that could harbor the ingredients for life. Scientists are eager to explore this alien environment, focusing on the search for biosignatures, indicators of past or present life. The icy surface, crisscrossed with dark streaks and cracks, tells a tale of a dynamic world. Beneath this frozen facade, the ocean is kept liquid by tidal forces from Jupiter, creating a potentially habitable environment. Future missions aim to penetrate this ice or study the surface in detail to find chemical signs of life, such as specific molecules or isotopes that could only be produced by biological processes. Titan, Saturn's largest moon, presents a different yet equally intriguing icy environment. Its surface is a frozen mosaic of hydrocarbons and water ice, with lakes and rivers of liquid methane and ethane. The search for biosignatures here is more complex, as any life would likely be based on different chemistry than Earth's. Scientists are particularly interested in the moon's subsurface ocean, which lies beneath a thick ice shell. This hidden water body could provide the necessary conditions for life, and future missions may use radar and other instruments to probe its depths. The search for biosignatures on Titan will involve looking for unusual chemical signatures that could hint at exotic life forms. Both Europa and Titan offer unique challenges and opportunities for the search for biosignatures. On Europa, The focus is on understanding the ocean's composition and dynamics, as well as the exchange of material between the ocean and the surface. Future missions may include landers equipped with sophisticated instruments to analyze the icy surface for signs of biological activity. Meanwhile, Titan's rich organic chemistry and complex surface features make it a prime target for astrobiological exploration. Scientists are developing advanced technologies to study Titan's atmosphere, surface, and subsurface, looking for clues that could reveal the presence of life. The search for biosignatures on these icy worlds is not just about finding life, but also about understanding the limits of habitability. By studying these extreme environments, scientists can gain insights into the potential for life elsewhere in the universe. The data collected from these missions will inform our understanding of the origins of life on Earth and the possibilities for life beyond our planet. Each discovery brings us one step closer to answering the fundamental question: are we alone in the universe? In situ resource utilization, living off the land. The icy moons of Europa and Titan present some of the most extreme and alien environments in our solar system. Europa, a moon of Jupiter, is encased in a thick layer of ice, likely hiding a global ocean beneath. This ocean, warmed by tidal forces from Jupiter's gravity, could harbor twice as much water as Earth's oceans. Titan, the largest moon of Saturn, boasts a dense atmosphere and a surface dotted with lakes and rivers of liquid methane and ethane, all under a chilly -179 degrees Celsius. These environments are not just scientifically fascinating, they also offer unique opportunities for in situ resource utilization, ISRU, where future missions could leverage local resources to sustain exploration. On Europa, the primary resource of interest is water. Extracting water from the icy surface could provide a vital resource for human exploration, but it also holds scientific value. By analyzing the composition of Europa's ice and ocean, scientists hope to find biosignatures, molecular patterns, or chemical signatures that could indicate the presence of life. These biosignatures might include specific isotopes, amino acids, or other complex organic compounds. The ice itself is a record of Europa's history, with layers that could reveal changes in the moon's environment over time. Accessing and studying these resources would require advanced drilling and sampling technologies, capable of operating in extreme cold and high radiation environments. Titan's resources are equally intriguing, though vastly different. The moon's atmosphere is rich in nitrogen and methane, which could be used for fuel production. The lakes and rivers of hydrocarbons on Titan's surface represent a vast reservoir of carbon-based materials. These could be processed into plastics, fuels, or even building materials for future habitats. The search for biosignatures on Titan focuses on different compounds than those on Europa. Here, scientists look for complex organic molecules that might hint at exotic forms of life adapted to Titan's cryogenic temperatures. The moon's thick atmosphere also offers protection from radiation, making it a potentially safer environment for human explorers than Europa. Both Europa and Titan present significant challenges for ISRU. The extreme cold, radiation, and distance from Earth require innovative solutions for resource extraction and utilization. On Europa, melting ice to access water would demand substantial energy, likely provided by advanced nuclear or solar power systems. On Titan, processing hydrocarbons would require sophisticated chemical plants, capable of operating autonomously in a harsh environment. Despite these challenges, the potential scientific rewards are immense. By living off the land on these icy worlds, future missions could unlock the secrets of their potential habitability and perhaps even discover the first evidence of life beyond Earth. Radiation, a constant threat. Radiation is an ever-present challenge for missions venturing into the outer solar system, particularly to icy moons like Europa and Titan. These celestial bodies, shrouded in ice and harboring subsurface oceans, are prime targets in the search for extraterrestrial life. However, their environments are bathed in intense radiation, posing significant hurdles for both exploration and the preservation of potential biosignatures. Europa, a moon of Jupiter, orbits within a harsh radiation belt. The planet's magnetic field traps charged particles, creating a deadly environment. The radiation dose on Europa's surface is akin to receiving a fatal human radiation exposure in just a few days. This intense radiation can alter and destroy complex organic molecules, making the search for biosignatures particularly challenging. Scientists must design radiation-hardened instruments and consider innovative ways to shield sensitive equipment. One approach is to use the ice itself as a natural shield, deploying landers or probes that can burrow beneath the surface. This strategy not only protects the instruments, but also allows for direct sampling of the subsurface, where conditions might be more hospitable for life. Titan, Saturn's largest moon, presents a different radiation scenario. While it lacks a global magnetic field, it is still exposed to cosmic rays and solar radiation. These high-energy particles can penetrate deep into Titan's icy crust, potentially altering any organic material present. Unlike Europa, Titan has a thick atmosphere, which provides some protection. However, the atmosphere also introduces its own set of challenges, such as chemical reactions that can obscure or modify biosignatures. To overcome these obstacles, scientists are developing advanced instruments capable of detecting subtle chemical signatures in the ice and atmosphere. For instance, mass spectrometers and gas chromatographs can identify complex organic molecules, even in trace amounts. Additionally, researchers are exploring the use of autonomous underwater vehicles to explore Titan's subsurface oceans, which are thought to exist beneath its icy crust. The search for biosignatures on these icy moons requires a multifaceted approach. Scientists must consider the unique radiation environments and design instruments that can withstand and operate in these conditions. For Europa, this might involve radiation-hardened electronics and innovative shielding techniques. For Titan, it could mean developing instruments that can detect and analyze complex organic molecules in the presence of atmospheric interference. By understanding and mitigating the effects of radiation, missions to Europa and Titan can pave the way for groundbreaking discoveries in the search for extraterrestrial life. The icy environments of these moons, with their subsurface oceans and complex chemistry, offer a tantalizing glimpse into the potential for life beyond Earth. Communication, bridging the void. The icy environments of Europa and Titan present unique challenges for communication, with their thick ice shells and vast distances from Earth. Europa, Jupiter's moon, is encased in a layer of ice that could be tens of kilometers thick, hiding a subsurface ocean that might harbor life. Titan, Saturn's largest moon, is enveloped in a hazy atmosphere and has a surface dotted with lakes and seas of liquid methane and ethane. These environments demand innovative communication strategies to relay data back to Earth. Radio waves, the backbone of deep space communication, struggle to penetrate these icy obstacles. On Europa, the ice shell could scatter or absorb signals, making direct communication from a subsurface probe to Earth nearly impossible. Scientists are exploring the use of relay systems, such as orbiters equipped with advanced antennas, to bounce signals between the surface and Earth. These orbiters would need to be highly autonomous, capable of navigating the intense radiation environment around Jupiter and maintaining precise orbits to ensure consistent communication links. Titan's thick atmosphere and distance from the Sun present their own set of challenges. The atmosphere scatters radio waves, requiring the use of higher frequency bands that can penetrate the haze. Additionally, the low temperatures and lack of sunlight limit the power available for communication systems. To overcome these hurdles, researchers are developing low-power, energy-efficient communication technologies. These include advanced modulation techniques that maximize data transmission rates while minimizing power consumption. Moreover, the search for biosignatures on both moons necessitates high-bandwidth communication to transmit detailed spectral and chemical data back to Earth. The search for biosignatures, or signs of life, adds another layer of complexity to communication needs. Scientists need to transmit high-resolution images, spectral data, and chemical analyses from these distant worlds. To achieve this, future missions may employ laser communication systems, which offer higher data rates than traditional radio systems. These laser systems, however, require precise pointing and tracking capabilities to establish and maintain links over vast distances. The development of such technologies is crucial for unlocking the secrets of these icy moons and understanding their potential to support life. Powering missions, nuclear versus solar. In the frigid, shadowed realms of Europa and Titan, powering missions presents a unique challenge. The icy environments of these moons, with their low temperatures and limited sunlight, demand robust and reliable energy sources. Solar power, while effective in the inner solar system, struggles to provide sufficient energy in these distant, dimly lit worlds. The sunlight that reaches Europa is about 1/25 th of that on Earth, and Titan, shrouded in a thick, hazy atmosphere, receives even less. Solar panels would need to be impractically large to generate enough power, making them less feasible for these missions. Nuclear power, on the other hand, offers a compelling alternative. Radioisotope thermoelectric generators, RTGs, have been used successfully in past missions, such as the Voyager probes and the Mars rovers. These devices convert the heat produced by the radioactive decay of plutonium-238 into electricity. RTGs are compact, reliable, and can operate for decades, making them ideal for the harsh conditions of Europa and Titan. They can provide a steady power supply regardless of the distance from the sun or the local environmental conditions. The search for biosignatures on these icy moons adds another layer of complexity to the power requirements. Europa's subsurface ocean and Titan's methane lakes and seas are prime targets for astrobiological research. These environments require sophisticated instruments to analyze samples and search for signs of life. Nuclear power can support these high-energy demands, enabling scientists to operate advanced instruments and transmit data back to Earth. Solar power, with its inherent limitations in these environments, would struggle to meet these energy needs. Moreover, the reliability of nuclear power ensures that missions can operate continuously, even during the long, dark winters on these distant worlds. The choice between nuclear and solar power thus becomes clear. Nuclear power is the more practical and reliable option for powering missions to Europa and Titan, enabling scientists to explore these icy environments and search for biosignatures effectively. Sample return, the holy grail of planetary exploration. Beneath the icy crusts of Europa and Titan, oceans of liquid water and hydrocarbons hide, potentially harboring conditions suitable for life. These icy moons, orbiting Jupiter and Saturn respectively, present some of the most compelling targets in our solar system for the search for extraterrestrial life. Sample return missions to these enigmatic worlds could provide unprecedented insights into their habitability and the possibility of past or present life. The allure of bringing back pieces of these distant worlds to Earth is immense, offering scientists the chance to study them in exquisite detail with the full suite of instruments available in terrestrial labs. Europa's icy surface, crisscrossed with dark streaks and fractures, conceals a global ocean beneath. This ocean, possibly twice the volume of Earth's, is kept liquid by tidal heating from Jupiter's gravitational pull. The surface ice is bombarded by radiation, creating a complex chemistry that could provide energy for life. A sample return mission to Europa would aim to collect material from both the surface and, ideally, the subsurface ocean. The challenge lies in navigating the harsh radiation environment and developing technologies to drill or melt through the ice. The payoff, however, could be monumental. Analyzing samples for biosignatures, molecular indicators of life, would be a primary objective. These could include specific isotopes, complex organic molecules, or even microfossils, if life exists or once existed there. Titan, with its thick, nitrogen-rich atmosphere and methane cycle, presents a different but equally intriguing scenario. Its surface is dotted with lakes and rivers of liquid methane and ethane, and there is evidence suggesting a subsurface water ocean. The chemistry on Titan is rich and diverse, with complex organic molecules raining from the sky and accumulating on the surface. A sample return mission here would target both the surface materials and, potentially, the subsurface ocean. The search for biosignatures on Titan would focus on different types of molecules than those on Earth, given the moon's unique chemistry. For instance, scientists might look for patterns of hydrogen isotope ratios or specific organic compounds that could indicate biological processes. The data from such a mission could revolutionize our understanding of the limits of life and the potential for life to arise in environments vastly different from Earth's. The technological hurdles for sample return missions to Europa and Titan are substantial. For Europa, the radiation environment necessitates innovative shielding and rapid mission timelines to minimize exposure. For Titan, the thick atmosphere and cryogenic temperatures demand robust entry, descent, and landing systems. Despite these challenges, the scientific community is actively developing concepts and technologies to overcome them. The potential rewards: bringing back samples that could contain the first definitive evidence of life beyond Earth, make these missions the holy grail of planetary exploration. The insights gained could answer fundamental questions about our place in the universe and the potential for life to exist elsewhere. International collaboration, a global endeavor. The icy moons of Europa and Titan have captivated scientists and space enthusiasts alike, their alien landscapes hiding potential secrets about the origins of life. These celestial bodies, with their unique environments, demand a global effort to unravel their mysteries. Europa, with its vast subsurface ocean beneath a thick ice shell, presents a tantalizing target for astrobiologists. The ocean, kept liquid by tidal heating from Jupiter, could harbor conditions suitable for life. Similarly, Titan, Saturn's largest moon, boasts a dynamic environment with lakes and rivers of liquid methane and ethane, and a complex chemistry that might support exotic forms of life. The search for biosignatures on these moons is a monumental task, one that transcends national boundaries and unites scientists from around the world. International collaboration is the backbone of these ambitious missions. For instance, the proposed Europa lander mission, a concept under study by NASA, would benefit immensely from global partnerships. European Space Agency, ESA, scientists bring expertise in ice-penetrating radar and advanced spectroscopy, crucial for analyzing Europa's icy surface and subsurface. Meanwhile, researchers from Japan and Canada offer unique insights into extreme environments and robotic exploration technologies. This collective knowledge pool enhances the mission's scientific return, ensuring a comprehensive understanding of Europa's habitability. Similarly, the Dragonfly mission to Titan, selected by NASA for its New Frontiers program, involves contributions from international partners. ESA's expertise in aerospace engineering and Russia's experience in planetary exploration add valuable dimensions to the mission's design and execution. The search for biosignatures on these icy moons requires cutting-edge technology and innovative approaches. On Europa, scientists aim to detect organic molecules and other signs of life within the icy surface or plumes of water vapor that may erupt from the subsurface ocean. Advanced instruments, such as mass spectrometers and Raman spectrometers, are being developed to analyze these samples with unprecedented precision. International collaboration plays a pivotal role in this endeavor, with scientists from diverse backgrounds contributing to the design and testing of these instruments. For Titan, the focus is on understanding the complex organic chemistry that might lead to the formation of life. The Dragonfly mission, equipped with a suite of sophisticated instruments, will explore Titan's surface and atmosphere, searching for biosignatures and studying the moon's potential habitability. This global effort ensures that the best minds and technologies are brought to bear on these challenging scientific questions. Moreover, international collaboration fosters a spirit of shared discovery and mutual respect. Scientists from different countries bring unique perspectives and approaches to the table, enriching the scientific process. For example, researchers from India and China have made significant contributions to the study of icy moons, offering fresh insights and innovative solutions. This collaborative environment not only accelerates scientific progress, but also strengthens international ties and promotes peace and cooperation. The icy environments of Europa and Titan, with their promise of groundbreaking discoveries, serve as a unifying force, bringing together scientists from all corners of the globe in a shared quest for knowledge. Public engagement, inspiring the next generation. The icy moons of Europa and Titan have captivated scientists and space enthusiasts alike, offering tantalizing possibilities for astrobiological discovery. Europa, with its vast subsurface ocean beneath a thick ice shell, presents a compelling target in the search for extraterrestrial life. The ocean is likely in direct contact with a rocky seafloor, creating a potential habitat for life as we know it. Titan, on the other hand, boasts a complex organic chemistry and a methane cycle that mimics Earth's water cycle, complete with lakes, rivers, and even rain. These environments, though alien, provide a rich tapestry for scientific exploration and public engagement. Engaging the next generation in these missions involves highlighting the thrill of scientific discovery and the potential to uncover biosignatures, indicators of past or present life. For Europa, this means discussing the exciting possibility of a subsurface ocean that could harbor life. The ice shell, which is estimated to be 1525 kilometers thick, presents a formidable challenge, but also an opportunity for innovative technology. Future missions, such as NASA's Europa Clipper, aim to study the moon's ice shell, ocean, and geology in detail, using advanced instruments to search for biosignatures. The public can be inspired by the prospect of drilling through the ice or using radar to map the subsurface ocean, much like exploring uncharted territories on Earth. Titan's unique environment offers a different but equally fascinating avenue for engagement. The moon's thick atmosphere and organic-rich surface provide a laboratory for studying prebiotic chemistry, the chemical processes that could lead to the origin of life. The Cassini-Huygens mission, which explored Titan extensively, revealed a world with dunes of organic material and lakes of liquid methane and ethane. Future missions, like the proposed Dragonfly drone, could further explore these environments, searching for biosignatures in the moon's atmosphere and surface. The public can be captivated by the idea of a drone flying through Titan's atmosphere, sampling its surface, and potentially uncovering clues about the origins of life. To inspire the next generation, it's crucial to emphasize the interdisciplinary nature of these missions. Studying Europa and Titan involves geology, chemistry, biology, and engineering, offering a wide range of opportunities for students and young professionals. For instance, understanding the ice shell of Europa requires knowledge of glaciology and planetary science, while exploring Titan's atmosphere necessitates expertise in aerospace engineering and atmospheric chemistry. By showcasing the diverse career paths and the collaborative efforts behind these missions, the public can be motivated to pursue STEM fields and contribute to future explorations. Moreover, involving students in citizen science projects, such as analyzing data from these missions, can foster a sense of ownership and excitement about space exploration. Ethical considerations, planetary protection. The icy moons of Europa and Titan, with their subsurface oceans and complex chemistry, present some of the most compelling targets in the search for extraterrestrial life. These environments, however, are also some of the most delicate, raising significant ethical considerations regarding planetary protection. The icy crust of Europa, for instance, is a labyrinth of ridges and fractures, concealing an ocean that might harbor life. Any mission venturing into this alien world must tread carefully to avoid contaminating this pristine environment with earthly microbes. Similarly, Titan's methane lakes and nitrogen-rich atmosphere create a unique chemistry that could potentially support life, making it crucial to preserve its integrity for scientific study. Scientists are particularly interested in the biosignatures that could be present in these icy environments. Europa's subsurface ocean, kept liquid by tidal heating, might contain hydrothermal vents similar to those found on Earth, which are known to support diverse ecosystems. Contamination from Earth microbes could obscure these potential biosignatures, making it difficult to distinguish between native life and terrestrial intruders. Similarly, Titan's organic-rich surface and atmosphere offer a tantalizing mix of chemicals that could potentially give rise to life. The Cassini-Huygens mission provided valuable data, but future missions will need to be even more cautious to avoid introducing earthly contaminants that could skew our understanding of this enigmatic moon. The ethical considerations extend beyond mere contamination. They also involve the responsibility to preserve these environments for future generations of scientists and explorers. The principles of planetary protection are not just about avoiding harm. They are about ensuring that the scientific value of these worlds is preserved. This means adhering to strict sterilization protocols for spacecraft and their components. It also means carefully planning missions to minimize the risk of accidental contamination. For example, the Europa Clipper mission, set to launch in the near future, will maintain a safe distance from the Moon's surface to avoid any potential contamination. This approach allows for extensive study while minimizing the risk of introducing earthly microbes. Moreover, the search for biosignatures on Europa and Titan requires a delicate balance between exploration and preservation. Scientists must be able to collect samples and conduct experiments without compromising the integrity of these environments. This is a complex challenge, as it involves not only technological solutions, but also ethical considerations. For instance, the use of robotic landers and subsurface probes must be carefully planned to ensure that they do not inadvertently introduce contaminants. The ethical considerations also extend to the interpretation of data. Scientists must be vigilant in their analysis to ensure that any potential biosignatures are not the result of terrestrial contamination. This requires a high level of scientific rigor and ethical responsibility. The future of outer solar system exploration. Beneath the icy crusts of Europa and Titan, two of the most intriguing moons in our solar system, lie vast oceans that could potentially harbor life. These icy environments, stark and alien, present a tantalizing opportunity for scientific discovery. Europa, a moon of Jupiter, is believed to have a global ocean beneath its ice shell, possibly with more than twice the amount of water as Earth's oceans. Titan, orbiting Saturn, boasts not only a subsurface ocean but also lakes and seas of liquid methane and ethane on its surface, making it the only other body in our solar system known to have stable bodies of liquid on its surface. The search for biosignatures in these extreme environments is a driving force behind future missions. Scientists are particularly interested in Europa's ocean due to its potential habitability. The moon's ice shell, which may be up to 15 miles thick, insulates the subsurface ocean from the harsh radiation environment around Jupiter. This ocean is thought to be in direct contact with a rocky seafloor, providing essential minerals and energy sources that could support life. Future missions, such as NASA's Europa Clipper, aim to study the moon's ice shell, ocean, and geology in detail. The spacecraft will perform flybys of Europa, using a suite of instruments to gather data on the moon's composition, geology, and the potential habitability of its ocean. One of the key objectives is to search for biosignatures, or signs of life, in the form of certain chemicals or patterns that could indicate biological processes. Titan, with its Earth-like cycle of liquids flowing across its surface, offers a unique opportunity to study a world with active chemistry and potentially complex organic molecules. The moon's subsurface ocean, hidden beneath a thick ice shell, is thought to be in contact with a rocky core, providing a potential energy source for life. NASA's Dragonfly mission, set to launch in the near future, will send a drone to explore Titan's surface and atmosphere. The drone will study the moon's dunes, lakes, and other features, searching for signs of past or present life. One of the key goals is to investigate the moon's organic chemistry, looking for complex molecules that could be building blocks for life. Additionally, Dragonfly will search for biosignatures in Titan's atmosphere and on its surface, providing valuable insights into the potential habitability of this enigmatic moon. As we conclude our journey through the icy realms of Europa and Titan, let's recap the thrilling possibilities that lie ahead. These moons, with their vast subsurface oceans and complex organic chemistry, are beacons of hope in our quest to understand the potential for life beyond Earth. Europa's frozen crust, scarred by mysterious streaks and towering ice cliffs, hides an ocean that could harbor more water than all of Earth's seas. Meanwhile, Titan's methane lakes and icy dunes offer a tantalizing glimpse into a world where life might have found a way to thrive in conditions vastly different from our own. Imagine the day when our robotic explorers break through Europa's icy shell, diving into the dark, alien ocean beneath. Picture the moment when we collect samples from Titan's shorelines, analyzing them for the chemical signatures of life. These are not just missions, They are odysseys that will rewrite our understanding of the cosmos and our place within it. As we stand on the brink of these extraordinary discoveries, we invite you to join us on this journey. Follow our missions, share in the excitement, and together, let's unravel the secrets of these icy worlds. The future of space exploration is not just about reaching new destinations. It's about answering some of the most profound questions in human history. Are we alone in the universe? What does life look like beyond Earth? The answers may be lurking beneath the icy surfaces of Europa and Titan, waiting for us to find them. Stay tuned, stay curious, and let's embark on this adventure together. The next chapter in our exploration of the cosmos is just beginning, and it promises to be nothing short of extraordinary.